Buonasera a tutti e benvenuti a questo secondo appuntamento con il tour digitale proposto dal Premio Cosmos, un premio appunto nato a Reggio Calabria, un incontro questa sera internazionale. Si svolgerà in lingua inglese, quindi fra poco ci sposteremo appunto inizieremo a parlare in inglese e abbiamo come protagonisti Sean Carroll dalla California e Amedeo Balbi invece da Roma, se non erro. Prima di dare la parola però ai due relatori di questa sera, vorrei dare il benvenuto a Gianfranco Bertone. Buonasera, professor Bertone, benvenuto, che ha ideato ormai 3 anni fa questo premio e che questa sera appunto ci presenta brevemente gli ospiti di questo secondo appuntamento e anche perché è nato il Premio Cosmos appunto nel 2018. Prego, benvenuto.
Grazie. Allora io passo all'inglese.
Assolutamente.
In inglese. So welcome to this event between finalist Sean Carroll and Premio Cosmos jury member Amedeo Balbi. I would like to start this with a very brief introduction to the Cosmos Prize. And I will just spend a few minutes introducing the Cosmos Prize and the authors, and then I'll let the two of them have this conversation on Sean Carroll's latest book, Something Deeply Hidden. So let me see if I can share this full screen. So this is, you should be seeing my screen now with the logo of the prize, and this is an initiative that's at the core of this initiative. There is the idea that science is for all. This is an initiative in collaboration with the Italian Ministry of Education, the city and the planetarium of the city of Reggio Calabria in the south of Italy, the Italian Astronomical Society, and 2 cultural foundations, Fondazione Con il Sud and Circolo Reggio Emilia. Science for All has 2 meanings here. 2 different but related meanings. The first one is that we want to promote outstanding science outreach by celebrating the authors who make science accessible to all, so really accessible for a large audience. And Sean Carroll is a perfect example of this type of endeavor. There's also a second meaning, which is that we want to engage all young people with science. We want to engage all. We want to focus in particular on young people, and we want to include young people with disadvantaged socioeconomic backgrounds. Okay, so this is the other meaning of Science for All. Every year we assign 2 prizes. The first prize is assigned by a scientific committee made of high-profile scientists active in popular outreach. And some of you might recognize some faces on this slide. And on the right, you see the 5 books that have been shortlisted for what is called the Cosmos Prize, assigned by the scientific committee. And in particular, you see the book of Sean Carroll that we're discussing tonight, Something Deeply Hidden. And there's a second prize, which is in line with the second objective of our initiative, which involves high school students. We involve every year hundreds of high school students in the selection, the debates, and the voting of the best prize in the fields of physics, mathematics, and astronomy. We help them, we send them a short list of books, and the students have the opportunity to read outstanding popular science selected for them by this scientific committee. They have an opportunity to debate and to discuss with teachers and fellow students about science. And they also have the opportunity to interact with the outstanding authors of the books that are sent to them. Tonight, we have we're very happy to have a conversation with finalist Sean Carroll, who's written this book. So the title that you see on this slide is the title in the Italian edition. The English title is Something Deeply Hidden. Sean Carroll is a theoretical physicist specializing in quantum mechanics, gravity, and cosmology. He's a research professor at the Waterbuck Institute for Theoretical Physics, the California Institute of Technology, Department of Physics, and external professor at the Santa Fe Institute. Amedeo Balbi is the member of the scientific committee of the prize, who will have this conversation with Sean Carroll about his book. Amedeo is also a scientist, associate professor at the University of Tor Vergata, and a very well-known author of popular science books. I should say that I'm very happy tonight. Sean and Amedeo are two of my favorite people. I read with equal interest the scientific research papers that they publish, as I do their popular science books. And I think I will stop here with this introduction. I just want to leave them enough time for this conversation. And I want to thank both of you, Sean and Amedeo, for being here tonight. And it's back to you. I think either Antonio or maybe Amedeo, you can directly start the discussion by introducing Sean Carroll's book.
Okay, so good evening, everybody. I hope you can hear me well. And I'm really happy to be here with Sean. I'm really a big fan of Sean books in general. And I'm really happy to discuss this book. I think it's a very ambitious book, and actually all of Sean's books are very ambitious. But in this one, I think he's trying to do at least 3 different things, and I hope I can give a good summary, but then Sean will certainly say something more about that. What he's trying to do is giving, first of all, a very nice and clear introduction to quantum mechanics for the layperson. And the second thing he does is he gives arguments in favor of an interpretation of quantum mechanics, or perhaps a theory of quantum mechanics, and then I will ask exactly what the difference is, but the many-world interpretation, or the many-world theory. And the third thing that the Sean tries to do and discuss is how we are trying to approach the problem, some of the open problems in theoretical physics these days, and in particular the emergence of space-time and the marriage between general relativity and quantum mechanics, which are big problems in theoretical physics. And this part of the book is the more, of course, is the most speculative, but it's very interesting because it's discussing very new and recent ideas. So I hope it sounds as a good summary, but I will leave perhaps Sean to tell something more about the book and the motivations behind the book.
Yes, thank you very much, Amedeo. Thanks very much to everyone. It's a great honor to be on the shortlist for the Cosmos Prize. I think that the 3 things that you mentioned as goals of the book are exactly right. I would add a 4th goal that the book has, which is to embarrass physicists about how little they have cared historically about the foundations of quantum mechanics. For those of you who are not professional physicists, this might seem weird, but we understood quantum mechanics in its present form around 1927, right? There was a famous conference, the Solvay conference in Belgium, where Einstein and Bohr and Heisenberg and Pauli and de Broglie and all these people were there. And they really sort of agreed on how to talk about quantum mechanics, except they didn't agree. People like Einstein and Schrödinger said, no, we're not done yet. We still have a ways to go to understand this theory. And for whatever reason, they lost. I mean, we're talking about Einstein and Schrödinger here, not like little people on the periphery, right? People who should get some respect for what they thought. But the other side, Niels Bohr and Heisenberg and Pauli said, nope, we have it figured out, quantum mechanics. Don't ask any more questions. Let's put it to work. Let's understand particle physics and field theory and things like that. And they won that side of the debate. And that side has sort of won for the last 90-some years. So I think it's finally time that we pick up the challenge that was laid down to us by Einstein and Schrödinger back in 1927. They thought that we weren't done yet. And quantum mechanics is enormously successful as a theory. It's clearly latching on to something true and correct about how nature works. Therefore, I would say it's even more important that we really, really, really understand it. Not understand it just sort of kind of well. What we really need to like figure out exactly what it's saying. There's so many unanswered questions about quantum mechanics that it's time now to do better.
Yeah, in fact, one of the things I liked about the books is the way it approaches the relationship, the difficult relationship between Einstein and Bohr, which usually is told as, you know, sort of a conflict between two different visions of the reality of the world in general and of physics. And you give a little a different take on this relationship and who actually won the conflict or the fight. And I like the fact that you, well, I can say you seem very sympathetic to Einstein and the urge that Einstein has on really understanding what's going on. And in fact, the title of the book is a quote by Einstein, something deeply hidden, that he was talking about something else, but the motivation is that it seems like he wants to really understand what's going on behind it all, and I think this is one of the motivation behind what you write.
Yeah, no, that's exactly correct. And honestly, I think that I came out of my research for this book and for other things, trying to understand the original debates about the origin of quantum mechanics, more impressed with Einstein than I ever was. I now think that Einstein is underrated. Even though he's pretty highly rated already, right? You know, but there's this story about Einstein that, you know, he helped invent special relativity. He invented general relativity, these wonderful theories of space, time, and gravity. He made foundational, important advances in the origins of quantum mechanics. You know, many of you might have heard that the Nobel Prize that Einstein won was for quantum mechanics, not for relativity. Einstein never won a Nobel Prize for relativity, but he basically was the first person to suggest that light is quantized into individual photons, particles, right? But then we tell the story that, you know, later in life, he has sort of lost touch. He'd become conservative. He wasn't willing to accept the new quantum revolution and all that. And I think that whole kind of narrative is basically nonsense. For one thing, he was younger than I am now at the time of the Solvay conference, so I don't like to say that he was an old man who was out of touch with the young kids. But also, I mean, like you said, his real push was not quantum mechanics is too crazy, it must be wrong. That was never his idea. His idea was always, the rules that you're telling me that are obeyed by quantum mechanics are fuzzy and ill-defined. It wasn't even fundamentally that he didn't like randomness or anything like that. You know, he was very quotable, Einstein. So he has lots of quotes that you can take out of context and use. And one of them, of course, was that he didn't believe that God played dice with the universe. But honestly, that was never his fundamental worry. His fundamental worry was he just didn't think the theory was complete. It was well defined. And, you know, I totally think he was right. I think that the physics community as a whole was kind of bamboozled and browbeaten by Niels Bohr and others to their detriment. And, you know, let's put it this way. We got away with it for many, many decades because there were so many questions yet to be answered about quantum field theory, you know, building up to particle physics and the standard model and things like that. So we could leave some of these foundational questions about quantum mechanics unanswered, and it was okay. It was good enough for what we needed. But these days, we're trying to build quantum computers. We're trying to understand the origin of the universe. We're taking quantum mechanics for its own sake much more seriously than ever before. We're not just putting it to work and then forgetting about it. So I think now is the right time to revisit these debates that Einstein and Bohr had and figure out what the right answers are.
Yeah, so we'll get to the interpretation of quantum mechanics in a moment. But first, let me spoil the beginning of your book for people who haven't read it yet. And you say, right from the start, you say, you don't need a PhD in theoretical physics to be afraid of quantum mechanics, but it doesn't hurt. And so why are we afraid of quantum mechanics? And I'm speaking about, you know, physicists in general. What is so scary about quantum mechanics?
Well, this is an excellent question. And, I don't want to be, I have fun with my friends, the other physicists, but I get it. There are good reasons why they've taken the attitude that they have. So I need to explain a little bit about quantum mechanics to explain what's going on.
Yes.
The fundamental difference between quantum mechanics and every other theory of physics is that in the rules we teach our students when we teach them quantum mechanics, some of those rules have to do with what happens when you observe a system, when you measure it, when you do the experiment, right? And of course, that's an important part of doing physics, observations and measurements and so forth. But no other theory of physics ever required special rules for that, right? Whether it was general relativity or Maxwell's electromagnetism or Newtonian mechanics, you have a system and you observe it. And that's all that there was to it. You could observe it badly, okay, but you could in principle observe it well as well. Whereas in the rules of quantum mechanics, we say that the system is described and evolves in one way when you're not looking at it, and then in a completely different way when you look at it, when you measure it, you observe it. Okay, so number one, what do you mean by measure or observe? Like, if that's true, if you need in the fundamental rules of quantum mechanics separate statements about what happens when you measure a system, the system is sort of all spread out before you measure it, but when you measure it, it collapses to one particular value and it's random and you cannot predict it deterministically, right? So what do you mean by making a measurement? What counts as making a measurement? When does it happen? How quickly does it happen? What is the physical interaction? And different of us have different ideas about what the answers are to that, but we don't agree on what the answers are, and that's embarrassing. Like, we should know what the answers are to those questions. And the other is the way that we describe the system. Is that supposed to be what the system really is? Is that what we're doing? Or is it just a useful tool to predict measurement outcomes, right? What is the relationship between the mathematical formalism and the underlying reality? And so physicists, these are two really important questions in my mind. But number one, it's hard to answer them, right? Like, we don't know. It's not easy to pinpoint an experiment we can do, right? If you say, I propose that a certain symmetry is violated, then there's an experiment you can do at a laboratory that will tell you whether you're right or wrong. But these questions are sort of harder to get your head around. I mean, maybe they're even philosophical. A lot of philosophers have been pushing forward the need to answer these questions. And number two, like I said, you can get pretty far without them. Like, okay, maybe I don't have an exact answer for what a measurement is or what the real world is, but it's good enough. Right? I know what to predict when I do an experiment at CERN at the Large Hadron Collider. I know that counts as a measurement. So what else do I need? And so I think that, physicists made a strategic choice to say, we're going to put aside these deeper foundational questions and focus on more practical questions that we can immediately answer experimentally. And I get that. I appreciate why you would want to do that. But fundamentally, I don't think it's good enough. I think that we are not in the business of physics simply because we want to predict experimental outcomes. We want to understand. That's why we're here. We're here to discover the true fundamental nature of reality. And we shouldn't be embarrassed to say that. We should proudly proclaim that.
Yeah, in fact, at some point you use this image of the oracle. Quantum mechanics is a bit like an oracle that gives the right answers, and they're fantastically right, but we don't know exactly what's going on behind the curtain. And
Right.
And in fact, I think when people ask me, for example, if I like most general relativity or quantum mechanics, and believe it or not, sometimes they ask it. I always say, it's a difficult choice, but I always say general relativity, but simply because I think we understand it better. It's a very necessary theory. Once you have the equivalence principle, all the rest is like, just deduction and it's very elegant, okay? But with quantum mechanics, you always have this feeling that it's a little bit messy, or there isn't the same necessity, and of course it's fantastically correct, but you have to accept it as it is, right? And so I won't ask you whether you like most. Well, actually, I'll ask you. Actually, do you like more general relativity or quantum mechanics?
So here's the answer I will give. I've written a textbook on general relativity, and I'm in the middle of writing a textbook on quantum mechanics. So it's a perfectly fair question to ask. And here's how I open both books. I open the book on general relativity saying, general relativity is the most beautiful physical theory ever invented. It is, to put it another way, it's the best course to teach when you teach general relativity.
Exactly.
For exactly the reasons why you just said. It's so beautiful. You just have these simple sets of principles and everything flows from that. And as the professor teaching this, you seem brilliant, right? Because like all the logical deductions flow and you're the master of them, and it's a wonderful experience. Quantum mechanics is not like that. It's really like, okay, well, today we're going to have to learn about special functions or something like that. And there's a bunch of rules, and I'm going to tell you them. Don't ask me why these are the rules. You're not allowed to ask those questions. But quantum mechanics is more important. Quantum mechanics is more fundamental. So I opened the quantum book by saying quantum mechanics is the most fundamental physical theory ever invented. In fact, I like to say that quantum mechanics, the invention of quantum mechanics, which took place roughly between 1900 and 1927, is the most impressive intellectual achievement in human history. And the reason why is not only because quantum mechanics is central to modern physics and our view of the universe, but also it is so different from what came before that you have to be extremely impressed with the ability of physicists of that generation to throw out everything they were taught and put in place something very, very different. You know, that's something any of us is going to be resistant to doing in the heat of the moment. But they did it. And over, less than 30 years, they were dragged kicking and screaming to these conclusions. But they set this enormously impressive precedent for all of physics to follow that. So general relativity is more beautiful. Quantum mechanics is more important. I'm not going to say which is my favorite.
Okay, but I see that you have a sympathy for quantum mechanics, actually. Certainly more sympathy for quantum mechanics than I have. And in fact, getting to the point of interpretation, I have to confess that personally, I've always been a bit agnostic about interpretation. I know them, I read about them, I had some fascination for some of them sometimes, and then I changed my mind, but I never committed to one in particular. And you already told us, in fact, that we should do that. We, as physicists, we should take the thing seriously. We should think about interpretations and the foundations of quantum mechanics. But you also take a very strong stance. You do commit yourself to one of them, which is the many-world interpretation. So I would ask to say why do you think that the many-world interpretation is the right one, and why do you think so?
Yeah, as you sort of alluded to very quickly before, maybe the word interpretation isn't the word we should be using anymore. It made sense in the 1940s or 50s, because we had these rules in quantum mechanics that we teach our students, but we didn't know what the words meant in the rules. So you need an interpretation. But these days, and I think that a lot of physics students don't get exposed to this fact, but these days we have honest to goodness physical theories that purport to explain the foundations of quantum mechanics. And one of them might be right, but they're different theories. They make different experimental predictions. They make different statements about the fundamental nature of reality. So I think that's why a lot of us prefer the term foundations of quantum mechanics rather than interpretations of quantum mechanics. We're not doing literary criticism. We're proposing real different physical theories, okay? And that's no knock against literary criticism, very important, but that's not what we're doing in the foundations of quantum mechanics. And a lot of the struggle is, as impressive as it was for the physicists of the first quarter of the 20th century to invent quantum mechanics, there's still a psychological struggle to really let yourself believe it, right? To immerse yourself in what quantum mechanics is saying. And part of that was that this, what we call the Copenhagen interpretation, the formalism that was set up in the 1920s by Bohr and his friends, draws a distinction between the quantum system you're looking at, like an electron or an atom or whatever, and you, the observer, right? There's a dividing line. There's literally a technical term for it, the Heisenberg cut between the big world of observers and the little world of quantum systems. And according to these rules, the big world of observers obeys the rules of classical mechanics. So observers are classical and the systems they look at are quantum mechanical. And so my favorite theory is the many worlds interpretation, which was put forward by a graduate student, Hugh Everett, in the 1950s. And he's another just super remarkable person. Like, the only thing he ever did in physics was the many worlds interpretation. Then he left the field. And I know that I, very naively, when someone does one good thing and then leaves, you think, well, maybe they got lucky. Maybe they're in the right place at the right time. But you read what Everett wrote, and he was clearly a genius. It's not just that he proposed the right idea. He knew exactly what the implications were. He knew exactly who he was up against and why. And he was like one of the, like, Amedeo, you know, like, your favorite theoretical physicist in the world. One of the great things about the geniuses of our field is they not only get it right, but they see everything, like all of the different things that it touches and what it means, right? And Everett was like that. And his great proposal was, look, and it sounds very simple in retrospect. I'm an observer. I'm made of atoms and particles. All of my atoms and particles obey the rules of quantum mechanics. Therefore, I should obey the rules of quantum mechanics, right? And so he says, well, what would happen if you did that? And I'm sure he was not the first person. Schrodinger also asked questions like this, right? But Everett had the courage and the vision to really see it through. And what he says is, what we teach our students is you have an electron that when you're not looking at it, it has a wave function, as we say, which is just a fancy way of saying it's sort of all spread out in different places. But then when you look at it, you only ever see it at one place. So Everett says, okay, let's just remove all these weird rules about observations and wave functions collapsing and probabilities. Let's imagine the observer also obeys the rules of quantum mechanics. We have an equation, the Schrodinger equation, which says what should happen if you let a big physical system interact with a little physical system. And what is the answer? And everyone agrees on what the answer is. The answer is that that electron that was all spread out becomes entangled with the observer. This is the wonderful phenomenon of quantum entanglement, which Einstein and his collaborators really emphasized around 1935, and then people forgot about for a long time until recently. And whatever it says is, what you get is a quantum mechanical description that says there's part of it which says the electron was here and the observer saw it there. There's another part that says the electron was somewhere else and the observer saw it somewhere else. And that's true for all the different places you could have seen the electron. Everyone agrees that that kind of quantum mechanical superposition of many different possible outcomes is what is predicted by the equations if you treat the observer as quantum mechanical. Everett's only move was, in some sense, therapeutic. He says, just believe it. Just accept that. Just don't go any further. Don't invent more rules to get rid of all that stuff. What you have in front of you is a description of many different copies of the world. The one world that you used to live in is now many, many worlds. There's a world in which you saw the electron here, and there's another world in which you saw the electron somewhere else. And these worlds will never interact with each other. They go their separate ways. They don't interfere. They don't dynamically affect each other's evolution. They're just completely separate. So Everett says to you, relax, accept this is the way the world is. You can't be influenced by these other worlds, but they're there. And if you accept that they're there, you don't need to invent all this spooky hocus pocus about wave functions collapsing and extra rules. It's just the same equation we've always had, the Schrodinger equation. Everything works out fine.
Yeah, in fact, I think one of the most common objections to many worlds is exactly the fact that you have all these other worlds, and so you have this ontological burden of all these other worlds to carry on, and also it seems like the most sci-fi, or how do you call it? Because you have all all these other universes where different things happens and there are copies of yourself and all this crazy stuff. But in fact, you make the point that this is the most austere kind of quantum mechanics, because it doesn't make all the other assumptions that all the other theories or interpretations make. Am I right in summarizing your message?
Yeah, no, that's exactly right. The many worlds interpretation, I think that second objection that you have, or potential objection, that it just seems very science fiction-y, right? It seems very speculative, very far removed from our everyday experience of the world. I think that's at the heart of why most people who don't like the Everett interpretation have this reaction to it. Because the first objection, which is the one they will say out loud, that it's sort of extravagant, you have all these worlds, that's just not a sensible objection. Like, honestly, the objection that it seems very far from my experience, that's okay. Like, that's a legitimate objection. We're going out on a limb whenever, as scientists, we propose a theory that is so different from what we see. I mean, maybe it's still the right theory, but it's legitimate to say, well, let's not go that far quite yet. But this idea that you're worried that it's extravagant to have all these universes, what you're objecting to is not the many worlds interpretation. What you're objecting to is quantum mechanics at all. Because quantum mechanics says that even though I can observe the electron at this position or that position or somewhere else, or even if the electron could be spinning clockwise or counterclockwise, quantum mechanics says that when you're not observing it, these systems are in a superposition of many different possible observational outcomes. It's not that there is one possible outcome and we just don't know it yet. It's that the system really is a combination of all these possible outcomes. And if you believe that that's okay when you refer to an electron, then you should believe it's okay when you refer to a person. And you should believe it's okay when you refer to the universe. It's just a matter of scale. There's no new stuff being put in. So you're exactly right. I make the point that the Everett interpretation is the most austere conceptually. There are no ideas, no equations, no parts of reality that are put into the Everett interpretation that are not there in other versions of quantum mechanics. All Everett does is remove some clunky rules about what an observation is and where a wave function collapses and so forth. So the implications are highly non-austere, but the theory itself is lean and mean and very easy to write down.
Yeah, I think that one of the reasons why people eventually, accepted all the weird things of quantum mechanics is that there are experiments, and so they have to face it. And so you take the double slit experiment or the wave particle duality or whatever, quantum teleportation, all these crazy things that perhaps they're crazy, but this is how reality works. So you have to accept it, and perhaps the point with many worlds is that people say, well, you cannot actually test it, and so I would like you to say a few words about this, because I think it is fair to say that at the moment we have no empirical reason to prefer one interpretation or theory of quantum mechanics over the others. I think it's fair to say that this is the way at the moment, right? But perhaps you don't agree. I don't know. I don't know what your position is about that. But in any case, the question is, do you think that there is a way to test different interpretations?
Well, let's put it this way. One of the ways that we typically talk about scientific theories is to ask whether they are falsifiable, right? Karl Popper, philosopher of science, put forward the idea that what makes a scientific theory a good one is that it sticks its neck out. It goes out on a limb. It makes a prediction with the feature that if you look for that prediction and don't find it, then the theory is wrong, right? Then the theory is falsified. So you need to be in principle falsifiable. Now, any good philosopher of science will tell you it's more complicated than that. That is not the final word, but it's a good, rough guide to how things go. So, of course, the Everett interpretation makes non-falsifiable predictions. It makes a prediction that there are other worlds in which you and I are having a very similar conversation, but not an exactly similar one, right? Not exactly the same. I can't test that prediction. But the point is, no one ever said that every single prediction has to be testable, right? I mean, nuclear physics makes the prediction that in the center of the sun right now, 2 protons are coming together and fusing together to make a deuterium nucleus, right? I can't test that prediction. It's at the center of the sun. But I can test other predictions of nuclear physics. So the point is, the question you should be asking is, does the theory you're proposing make any falsifiable predictions? And remember, all the Everett interpretation is saying is that there is a wave function for the universe. It obeys the Schrödinger equation, the one equation that is constituent of quantum mechanics. And it doesn't obey any other equation. So the Copenhagen interpretation or other versions of quantum mechanics, Roger Penrose has interpretations of quantum mechanics, for example, they very often say that under the right circumstances, the Schrödinger equation is violated. The whole process of wave functions collapsing when you observe them is a violation of the Schrödinger equation, whereas Everett says everything always obeys the Schrödinger equation. So all you have to do to falsify the Everett interpretation is see a wave function collapse without you poking it. Just see it collapse all by itself, right? And there are not only theories that predict that will happen, there are experiments going on right now to look for it. So if those experiments come along and show that, yes, here's a physical system where the wave function is just collapsing all by itself without us interacting with it in any way, then Everett and the many worlds interpretation will be falsified right away. So it fits every single possible criterion you might want to imagine for me, a good, respectable, falsifiable scientific theory.
Okay. Okay, let me get to a few things that you discuss in the book at some point, and I found them very interesting because they were more philosophical in nature. They were touching on different aspects of reality that are not directly related, to just the simple fact of doing experiments and other things. But at some point, you discuss the question of free will and ethics and what to do with all the other copies that exist in the other universes. And then you discuss also consciousness and the relation. And we know that there is a problem with that because, people always, speaks about consciousness and quantum mechanics as if there is some special relationship between the two. And so I would like you to say, if you want, a few words about these different aspects and different implications that are not necessarily, related to laboratory experiments, but are more wide ranging.
Yeah, no, I think it's actually important to talk about this kind of thing. I learned this from Martin Rees, actually. Martin Rees, the great theoretical astrophysicist in Cambridge. I heard him give a talk one day about cosmology, a popular level talk that I thought I would just go to pick up some pointers from one of the masters. And in the middle of the talk, he started talking about extraterrestrial life on other planets. And I was, a little bit outraged. I'm like, why are we talking about life on other planets? It's supposed to be a cosmology talk, right? And the point was, the people in the audience didn't see this strong distinction between cosmology and life on other planets. To them, it's what they wanted to hear about. And so he actually gave people what they wanted to hear. And I think that as physicists, we know what we have in mind when we envision writing a book about quantum mechanics. And it's not talking about free will or consciousness. But there are a lot of people out there who care about these things, and they do link them to quantum mechanics. And so it's perfectly good to talk about that, answer the questions that people actually have. So a very interesting question is about ethics and morality, right? And free will, for that matter. Like, all of these come up in the same kind of sense, because you say to yourself, well, if everything I could possibly do comes true in some universe or another, then what's the point? What does anything matter to my life, right? Why do things I struggle to achieve matter if in some other universes I will or will not achieve them without struggling whatsoever, okay? And this is an interesting, there's two responses to this. One is, what you're really complaining about is not, or worried about, is not many worlds. It's the laws of physics. So, if classical mechanics had been true, right? If there were no such thing as quantum mechanics, if we were in the 1800s and we believed in classical mechanics, we all know this is a deterministic theory. There are laws of physics, right? So if you believe that human beings obey the laws of physics, then your struggles, your choices that you're making, are just ways that you and I talk about the fact that we have incomplete information about the universe. If we had perfect information, if we had the God's eye view of the universe, it's a clockwork universe, and you could predict exactly what would happen. It's deterministic, okay? And the Everett interpretation is exactly like that. it's deterministic. It just says that many different things happen. And so would you have had these same worries in classical mechanics that you now have in quantum mechanics? And I think it's really just a reflection of the fact that as much as you tell them or us that we are physical systems, we human beings, we obey the laws of physics, we still kind of think of ourselves as better than the laws of physics, right? We think that, the laws of physics are not telling me what to do. And, I think that's okay in a real sense, because I think that even though the laws of physics do tell me what to do, I don't know what they're telling me, right? I don't know what, in no realistic sense, do the laws of physics constrain my ability to make choices, because I have no idea what the choices are that I'm going to make. So I think that we need to draw a distinction between the fundamental physical description of reality in terms of classical mechanics or quantum mechanics or whatever, versus our human scale world, where we talk about ourselves as people that listen to arguments for and against, doing different things, and we make choices on that basis. These are compatible descriptions, but let's not mix them up together. The other thing that is unique about many worlds is that everything happens, right? That was not true in classical mechanics. And so that's a new worry that creeps in. But what matters there is if many worlds is to make any sense at all, even if everything happens, which is not quite true, everything that is allowed by the Schrödinger equation happens. Not everything. There are things that don't happen in many worlds, but many things do happen, but they don't count equally. Okay, this is a crucially important part of quantum mechanics. When quantum mechanics says, I can't predict exactly what's going to happen, but I can predict that something is going to happen with a 99% probability and the other thing is going to happen with a 1% probability. In many worlds, both things happen, but one thing counts more. Okay, so to make sense of this theory, you have to buy into the idea that it's not true that some things happen and some things don't. Everything happens, but some things count more. They count more for everything. They count more for making predictions. They count more for being happy or sad about whether or not you have landed in one of these worlds or not, in being ethical, being moral, all of these questions. You have to count the worlds unequally depending on what the quantum mechanical system is doing. If you deny that, then you just deny all of Everett's view of the world, which, okay, so then you're not in that many worlds kind of paradigm. But if you don't deny that, if you accept that the worlds count differently, then where you end up is all of your choices, all of your ethics, all of your morality are exactly like they should be in a world that is truly random and stochastic with the probabilities predicted by quantum mechanics.
And also you say, I guess, that not everything that happens has to do with the collapse of the wave function or whatever you want to call it. So unless you have this universe splitter application on your iPhone and you take decision by actually having a photon or some particle doing some quantum stuff, you don't take decisions. Your decisions are not directly related to a ramification of the wave function every time, right?
No, that's exactly right, and it's very important. When you are stuck on a decision, should I ask this person to marry me or not? Okay, that decision-making process does not branch the wave function in the universe. It's not like a movie where there's a world in which you get married and a world in which you don't. Okay. It's the other way around. It's quantum mechanics might influence your decision-making, but your decision-making does not influence quantum mechanics. So it is conceivable that in your brain, there are unlikely quantum mechanical fluctuations that force you in one branch of the wave function to make a different decision than you would in most of the wave function, okay? But what that means is that the decisions are not weighted equally. And so just like we said, if you feel like you have a decision that you're pretty confident about, that you've gone through all the rational decision making and done the best you can to make a choice, then it's probably true that that's the choice you make in the overwhelmingly large part of the wave function of the universe. And you shouldn't worry about the little part where you made a random dumb decision. Don't worry about that. That way lies madness.
Yeah, and also to close the loop, consciousness, as far as we know, has nothing to do with the ramification of the wave function or the worlds, right? It has nothing to do with with the collapse of the wave function, or again, whatever name you want to call it. And it doesn't have to do
again,
with...
There are good reasons, or there were good reasons back in the day, to at least ask the question, is consciousness somehow related to quantum mechanics? Because the rules that we were handed down by Niels Bohr and his friends have words like observer and measurement in them. And so you're asking yourself, well, what counts as an observer or as a measurement? Maybe one possible answer is observations are only carried out by conscious observers. And there are still people who believe this today, some of my best friends, honestly. But people, looked into that. And like I said, we know a lot better now than we did back then. So I can't say for sure that they're not related. But what I can say for sure is that we have perfectly good, promising theories in which they're not related. There's no relationship between quantum mechanics and consciousness. And Everett, the many worlds approach, is one of them. All of these questions that I mentioned at the beginning about what is a measurement, what counts, what kind of physical system can pull it off, these are all answered in the Everett interpretation. And the answer is just whenever any tiny quantum system becomes entangled with some big macroscopic system, that's when a measurement happens. It has nothing to do with consciousness. It could be a rock doing the observation, a video camera, whatever. So all of the worries about human agency and volition and consciousness somehow either affecting or being affected by quantum mechanics go out the window in this particular approach.
Okay. One last question I would make now is about the third part of the book that we haven't discussed, but it's arguably is the most speculative and also perhaps the most technical one in a sense. Although the book is not technical, is non-technical, but the topic is technical, and it is the way people, theoretical physicists, are trying to come up with some ideas for having quantum gravity, or describing what space-time actually is, and so on. So how do you address this problem, and what is the reason why you think that the many world interpretation has something to say about that?
Well, we could talk for hours about this one.
Yeah.
It's one of my favorite topics to think about. And again, for those of you who are not familiar with how physicists talk about this stuff, once we have a theory of some phenomenon, okay, a spring on a ball on a spring, or a ball rolling down a hill, or the electromagnetic field, the general way that we go about our jobs is to construct a classical version of the theory that would have been right in Isaac Newton's world, and then we quantize it, right? We promote it to a quantum mechanical description. And this particular procedure works for almost all of known physics. In particular, it works entirely for what we call the standard model of particle physics, the theory that explains the particles of which you and I are made, the electrons and the quarks, and all the forces that push them around, electromagnetism and the nuclear forces, etc. Okay? And so we think that, this is a pretty promising thing. You start with the classical theory, you quantize it, you get where you want to go. But it doesn't seem to work for gravity. Gravity is a very important force. It keeps us on the ground, right? Einstein told us how gravity works on large scales in his general theory of relativity in 1915, beautifully confirmed over and over again in cosmology and astrophysics. Now we're seeing gravitational waves. It's all very exciting, but it seems to resist being quantized, okay? And this has led people to sort of invent different theories that are not quite general relativity, like superstring theory, for example. Maybe quantizing them will explain gravity in some way. But it occurs to me and other people, nature doesn't start with a classical theory and quantize it, right? Nature presumably just is quantum mechanical from the start, and there's some limit, some approximation in which classical mechanics is a pretty good, although imperfect, description. So maybe the reason why we're not having success quantizing gravity is because we shouldn't start with the classical theory and then quantize it. We should just look for the phenomena we care about in quantum mechanics itself, in intrinsically quantum mechanical systems rather than classical systems that we're trying to promote. And I think that's one sort of statement we could argue about, but I think it's at least an interesting way of pursuing it. And the version of quantum mechanics that is ideally suited to this program is the many worlds interpretation of quantum mechanics. And the reason why is because, like we said, many worlds is austere, right? It has the fewest ingredients you put into it. You have a quantum mechanical system and it obeys the Schrodinger equation. That's it. Every other approach to quantum mechanics at a fundamental level has extra ingredients, either extra variables or extra rules or extra interpretive strategies or something like that, okay? So if you want to ask a question, let's start with a fundamentally quantum system and see what emerges out of it without prejudicing your idea of what should emerge out of it, then many worlds is perfectly set up for that. So I'm very optimistic, actually, that by taking the foundations of quantum mechanics seriously, by thinking about quantum mechanics quantum mechanically rather than classically and then upgrading, we'll have new insights onto how gravity and space-time really work.
Great. Okay. Yeah. I think Gianfranco wants to.
If I may, Sean, just ask you another maybe more general question, because you're also a well-known cosmologist, right? You have thought about cosmic mysteries, not only about the fundamental aspects of quantum mechanics, but also what we know about what we do not know about dark matter and dark energy and all the cosmic mysteries, inflation, and so on. And sometimes there's the impression that we are a bit stuck. On one side we have this kind of desert. We have these standard models of particle physics and cosmology that work very well, so well that it's very hard to break these standard models, right? With any observation, all the experiments we performed so far seem to be perfectly consistent with these two models. So on one side we have this desert, and on the other side we have this abyss of quantum gravity, and the search for really the fundamental theory, if there is one, more fundamental theory of physics. So what do you think? Do you think we're making progress on those two fronts? And this is also in line with some of the questions we received through social media. Where do you think we will see progress in the next decade, say?
No, this is an excellent question and a tricky one, because different people are going to give different answers depending on their intuitions, right? Like, none of us has immediate unalloyed access to the correct way of doing particle physics or cosmology or anything else, right? We have our individual proclivities, and that plays into how we act. There's a sense, as you say, that we're stuck in fundamental physics, but it's a pretty good notion of being stuck. I mean, we're stuck because our theories are so good, right? We have these wonderful theories that fit all of the data, but we don't think that they're the final theories. We don't think that they're completely the final answer to the entire story of nature. So, actually, theoretical physicists like it when their theories don't fit the data exactly. That means that we have some clues from nature about how to go beyond that. And right now we're in this weird, unprecedented situation where our theories are too good. To the extent of the data we have, we can explain most of it within our theories. And so, as I said in different places, I can imagine 3 different strategies for the working theoretical physicist when faced with this kind of conundrum. One is you just keep moving forward, right? You just keep trying your best. You invent new models, you do new experiments. The thing about being stuck is you're stuck until you're not stuck, right? Like, any day there could be a remarkable discovery or a remarkable insight that changes everything and that really moves us forward. So you can't give up on that old-fashioned, approach that has worked for the whole last 100 years, even if progress seems to be a little bit slow now, okay? The second option is you can say, you know what, I don't want to do this anymore. I'm going to do biology or, economics or something like that. So that's fine. I'm just not personally motivated to do that. I think that physics is still incredibly interesting. And the third strategy is to take a step back, is to say, well, okay, our theories are very, very successful. There's certain individual puzzles we have: dark matter, dark energy, the Big Bang, and we've banged our heads against them for a while. I know I have. But there's also these more foundational questions. So there's questions about the nature of quantum mechanics, about the nature of probability, the anthropic principle and things like that are good questions. There are questions about the nature of statistical mechanics and the arrow of time and things like that, how complex systems evolve. So there's a whole bunch of sort of bigger quasi-philosophical questions that are also hard to make progress on, but for different reasons. Not because we think we have good theories, but because we're not sure how to make progress. So that's my particular favorite thing to do. That's what I've been doing for the past 5 years, which is just to say, look, we have these wonderful, amazing theories. They're not the final theories. It's hard to see what direction to move in to make progress toward the final theories. I'm going to step back and dig in deep into the sort of foundations of all these things to see if maybe there's an angle or there's a sort of way of thinking about these things that we've been ignoring because other strategies have been so successful. In the perfect world for me, in the most optimistic world, this idea of emerging space-time from quantum mechanics is an example of how you have a new approach that is sort of inspired by not just pushing forward on the puzzles, but by stepping back and seeing, well, how does everything fit together in an interesting way? Whether or not it will turn out to be a good strategy, that's ask me that 20 years from now when I write another book and get on the short list again.
Perfect. Fantastic. Thanks a lot. Thanks a lot, Sean. There are more questions coming in from the social media, but I think I see that we are already 1 hour in the event, and I know you're a busy person, Sean, so we don't want to keep you for too long. Thanks a lot for this conversation. Thanks a lot to you, Sean. Thanks a lot, Amedeo, for moderating this event. I think, Sean, you might have converted some more people to the many words gospel this evening. Thanks again for your brilliant book, and thanks, Amedeo, again. And before closing, I wanted to remind everyone of our next meeting. As you will see, Sean, you're in very good company in the short list. If you can send project the slide. Yeah, perfect. Thanks, Antonio. So the next meeting will be between Brian Green and Carlo Rovelli, and it is on Thursday, the 8th of April at 6:30 p.m. Central European Summer Time. Thanks again to everyone. Take care.
Thanks, everybody. Stay safe.
Bye-bye.